So hello again guys, here we have question number 3 from Challenger Understanding exercise of the chapter Kinematics from Pathfinder. So it's an easy problem. I would suggest you all to try it once before looking at the solution. So first let's look at this question. Starting from the center of a circular path of radius r, a particle p chases another particle q that is moving with a uniform speed v on the circular path. The chaser p moves with a constant velocity of constant speed u and always remains collinear with the center and the location of the chased particle q. So the part A of the question is, on which path will p eventually move and how long will it take to reach on this path? And we have to consider the cases u is less than v, u equals to v, and u is greater than v. And for part B, if the speeds of the particles are v equals to 4 meter per second, u equals to 8 meter per second, and the radius of the circular path r equals to 84 meter, how long p will take to reach q? Use pi equals to 22 by 7. So if you want to try it yourself once, you can do it now. So now let's look at the hint. So the hint is p has the same angular velocity as q, so think what will be the radial velocity in the steady state. So if you want to try it again with this hint, you can do it now. So now let's look at the solution. So first of all, we have to observe that it has been said in the question that the particle moves on the line joining center and q, so it must have the same angular velocity as q. So it is very clear that it has the same angular velocity, so there's no problem in this. So now what we can say is, and as it eventually moves away from the center, its radial velocity will decrease and will eventually tend to 0. So finally, it finally settles in some steady state having no radial velocity because its velocity tended to 0 in the radial direction, and hence moving a concentric circle with q with the same angular velocity. So the three cases are shown here. Like in the case when u is less than v, it will set at a radius which is less than capital R. In the case when u equals to v, it will settle in the same circle of the radius r equals to capital R, and when u is greater than v, we get an radius which is greater than r. So now just as I said, equating the omegas for two cases, and here I have assumed r is the radius of the stable orbit in which it settles, so we get its radius to be capital R times u by v, although we don't need it, but it just might help in the second part. So this was this was the part 1. So now let's look at part 2. So now what we can observe is that p meets q only in cases 2 and 3, and likewise we have been given velocities of u and v such that u is greater than v. So we have to consider the third case to find the time in which they meet. So here we can see that as the particle moves outward, in the first case it is settling in this orbit itself, so it is not reaching this particle q. Similarly, in the second case, it just reaches the particle q. So in here we can consider the particles colliding with each other, or if you let them pass through it, so it will move. They will move in the same radius path. And similarly, in this case, it moves out of the radius. So in this is the case we have to consider in part 2. So from here, I've assumed that let's say when the particle is at a distance x from the center, when it has reached a distance x from the center, I have assumed its tangential velocity to be ut and its radial velocity to be ur, and the velocity of the particle q is v, which is constant. And we have to notice that the speed of particle p is constant, which is u, as it was said in the question. So the equations we get from here are ur squared plus ut squared equals to u squared, because the total velocity is constant to be u. So from here, what we can calculate, what we can say is that ur equals to u root of u squared minus ut squared, and we can write ut to be omega times r. So here r is x at this instant. So the radial velocity at this time will be u square root of u square minus omega x whole squared, and we can write the omega as the omega of the both the particles is same. This omega should be equal to the omega of the outer particle q, and the omega will be v over capital R. So substituting that, we get ur equals to root of u square minus v by r times x whole squared, and ur can be written as dx by dt, as it is in the increasing direction of x, and it is the rate of change of x, So from here dx by dt equals to u square, this value, and on separating variables we get this differential equation, and on integrating this from x equals to 0 to r, for collision it will move from a radius of initial radius of 0 to a final radius of r at the time of collision, and a time varying from 0 to t. So integrating this is a simple integral of sine inverse on the LHS. So this integral leads us to r by v times sine inverse vx by ur, and substituting the limits of r and 0, we get the time period t equals to r by v times sine inverse of v by u. So yeah, this is the final answer, and on substituting the values we get t equals to time period to be equals to 11 seconds. So yeah, that's the final answer for this question. So hope you all like the video. If you liked such content, please do subscribe and share it with your friends. Thank you.